pleasure to have Laura back, and she is going to be telling us today about on Cayley and Langlands type correspondences for Higgs bundles.
Thank you, Steve. It's nice to be back in Champagne and to be part of the seminar series. Big honor to be part of it. So what I want to tell you today is about some work that I've been doing, and I was debating whether to give you details about this recent paper that's from a couple of months ago, whose title is the title of the talk, about these type of correspondences between Higgs bundles, or maybe just to tell you how they all fit together within a global picture. So I'll do part and part of both, and I'll tell you how the details fit together, but I'll try to motivate it in a bigger picture. Since not all of you work on Higgs bundles, I'll just remind you of Higgs bundles and these type of correspondences that exist. Okay? You should stop me anytime that you feel you'd like more details, please. I'm not going to give too many details, but you should definitely stop me. So the plan will be to first put Higgs bundles into context. You'll probably all heard many talks about Higgs bundles, so I won't take too long, but I want to set the notation. And then I want to tell you about the correspondences that exist between Higgs bundles, and in particular between subspaces of Higgs bundles. So it's not all Higgs bundles that I'm going to be caring about. I'm going to care about some subspaces of them, and then I'll tell you about some applications of these correspondences. And when putting it into context, I'll try to match up with different questions that we could be asking that are still open questions in relation with Higgs bundles and these correspondences that exist. So along the talk, I'm going to be working on a Riemann surface, going to call it sigma, a compact Riemann surface of genus at least 2. And I'm going to be using the canonical bundle a lot, so I'm going to give it a name. K will be the cotangent bundle of our Riemann surface. And the Higgs bundles that we're going to work on, whilst defined here, we could try to attempt and put it on genus 1 or genus 0 and put mark points. And the same questions would apply. Most of them are not answered yet. So let's recall that what Higgs bundles are. So has everyone seen Higgs bundles before? Yes.
But it's okay to.
It's okay to recall?
Yeah.
I don't want to bore you. No. Okay. So I'll recall just briefly. So I'm going to also be using a group. So let me call GC complex Lie group. So recall that originally Higgs bundles was introduced back in '87 by Nigel Hitchin when studying self-duality equations, where a pair, so a Higgs bundle is a pair E phi on the Riemann surface where E for E vector bundle, holomorphic vector bundle on sigma, and phi holomorphic section that goes from E to E tensored with K. Holomorphic. And these are the generic classical Higgs bundles as first introduced, but the same way we can extend the vector bundle to be a principal bundle, we could ask what is a Higgs bundle for a principal vector, for a principal bundle. So what happens when we put a structure group to these objects? Here we're having a map, a holomorphic map, that sends a bundle to a bundle tensor with a line bundle, so one forms. So over each point of your surface, you're thinking of a vector space over each point, and a map that sends vector spaces to vector spaces. So really it's a matrix. We're going to be working a lot with matrices. So an example, that's the classical example that we want to keep in mind when thinking about these matrices, is the following. Just take your E, choose the square root of your canonical bundle. This canonical bundle has degree 2g minus 2. We can choose a square root, and we can sum it to its dual. So once we fix the square root, we fix one of the 2 to the 2g choices, we sum it to its dual, and now we construct a Higgs pair by taking phi. We said it was a matrix that sent a rank 2 vector space to a rank 2 vector space over each point of the surface. So it's going to send rank 2 to rank 2. I'm going to put it off diagonal, 0, omega, 1, 0. And when we have to think how does this Higgs field behave, what is the k to the half plus k to the minus a half to k to the half, k to the minus a half doing? So this is the structure that we had mentioned in the definition. This omega that appears here is going to be sending k to the minus a half to k to the half to k. So really this omega is a section over the Riemann surface of k. So we're putting this one with the opposite sign, sum with this one, so 1/2 plus 1/2 plus 1, so square. So it's a quadratic differential. And if you think about this one is here because we're doing the complementary thing, and it's just the identity. So this is a family parametrized by quadratic differentials. And when we generalize these to principal bundles, the only thing that I want you to think about here is that we can define GC Higgs bundles, so GC Higgs bundles, and the only thing that you need to consider is you need to consider your original definition and add some conditions reflecting the nature of GC. So taking the classical E phi and add conditions, so plus conditions.
So you're thinking of GC as a subgroup of SLNC.
Right, so that's, or GLN, really. Yes, so the groups that we're going to take and type A, B, C, D, let me put here. So classical Lie groups, for those classical Lie groups, you can add conditions reflecting nature of group. There is a formal definition, I just don't want to go through it, since what we're going to be doing is a lot of linear algebra too, and for that we need the matrix representation. So what do we mean, for example, if we took SL and C as our group, what we were asking is take E phi such that what? Such that the vector bundle E is rank n with trivial determinants, so top exterior power being trivial, and the trace of the Higgs field is 0. If you were to ask a special, for instance, the symplectic group, you would ask for the vector bundle to be of that rank, and the vector bundle to have a symplectic form, and the Higgs field to be compatible with that symplectic form. The same for orthogonal, etc. So we can go back to our example before moving on and try to figure out whether there's any condition we can see explicitly here. And here we can note, what we note is that this vector bundle that we took, it's a line bundle plus its dual. So when we took the top exterior power, so lambda 2 of E, top exterior power is trivial, and the Higgs field indeed is traceless. We build it that way. So this family that we said, a family parameterized by quadratic differentials, is actually of SL to C Higgs bundles. And we're not going to go through the real case, but we could also put a real group here and put extra conditions reflecting the nature of the real group. In that case, when we do it in this setting, we'll actually see that these would be SL2R Higgs bundles. And if you've seen Hitchin's work on Teichmuller spaces and the parametrization of Teichmuller space through the Hitchin components, those are the components for rank 2. So that's how it fits here. So these are the Higgs fields and vector bundles we're going to work with. We're going to take this definition. We're going to, whenever thinking about complex groups, we're going to take this perspective, and we're going to work with the moduli space of these objects, remembering that we have pointwise matrices and that we can do things to the matrices. Okay? So I want to take that moduli space and I want to introduce one of the main tools we're going to use to study that moduli space, and which leads to many of the applications that we have in mind. So the moduli space of Higgs bundles, I'm going to call it MGC. The moduli space of Higgs bundles. So moduli of, and this is of isomorphism classes of polystable or appropriately stable Higgs bundles of GC Higgs bundles. And this moduli space, which you can construct through a quotient, or you can construct in different ways, and you can study it from different perspectives, but the way that we're going to use today a lot is through the Hitchin fibration. So it has a fibration, H, and I'm going to call it to a base A that will depend on the group. So we can study it. We can study the moduli through the Hitchin fibration, which is the fibration H, that I call here H. This is the Hitchin fibration, and which you obtain in the following way. What you're doing is you're taking a representative of your class, so a Higgs bundle E5, and what you're going to do is you're going to create a cover of your Riemann surface through the eigenvalues of phi, and you're going to create the fibres by looking at the eigenspaces. So you're going to map it to eigenvalues, and the fibres of the map, fibres will be eigenspaces. So over your Riemann surface that you had originally, you're going to have a cover that will be given by your eigenvalues. So here we have sigma. Here we're going to have S, the cover. And these eigenvalues, we can write it really, how do you get eigenvalues from a matrix? You get it from the characteristic polynomial. So S will be defined as the zeros of the determinant of phi minus lambda times the identity. So that's the characteristic polynomial. That will give us a cover that we're going to call spectral curve. And the fibres, we said the fibres will come from the eigenspaces. And the eigenspaces on that cover, what we're going to have, is we're going to have eigenspaces which are generically one-dimensional, and which, when pushed down, they'll get together, and they'll get n-dimensional if we have an n cover. So if this is an n to 1, we're going to have line bundles here as the eigenspaces, and we're going to push them down to get pushed down to get E, the rank n bundle. So roughly speaking, this is what's going on. You have over your Riemann surface, over each point of your Riemann surface, you have your Higgs bundle. Your Higgs field is a matrix. You're looking at the eigenvalues of your matrix. You're constructing a cover. Over each point of your Riemann surface, you have these eigenvalues. You construct your cover. Over each cover, point of the cover, you have your eigenspace. And then you push down those to recover your bundle. Now, what are the properties of this map? Because it looks quite geometric how you define it, but it has very nice further properties. So the Hitchin fibration through the map H, say via projection H, via H, where this is again work by Hitchin from '87, his second paper that year on the subject, where he showed the following. So the map H is proper, which means that the inverse image of a point, a compact space, will be compact. So your fibres will be compact. And in particular, so it will be proper, and in particular, the generic fibres are compact abelian varieties. So we just saw the hint of this happening because we said our fibres will be the eigenspaces, which are line bundles. And what is this? This is the Jacobian of that curve. Line bundles of degree 0 is going to be the Jacobian. If we change the group and we add some conditions to reflect the conditions of the group, then what we'll get is compact abelian varieties inside Jacobian. So there are compact abelian varieties given by the Jacobian of S, if we are in the classical case, or subvarieties, so abelian subvarieties for other groups. So this is what we call spectral data description of Higgs bundles, and we're going to be using it a lot. Are there any questions about this? What I'd like to do next, since now we have all of the objects we want to work with, we have our Higgs bundles, we have our moduli space, and our Hitchin fibration. The next thing that I'd like to tell you is about how the type of questions that I'm asking appear, and which questions are still open, and which ones we're going to address with these correspondence. For that, we're going to use this fibration of the moduli space of Higgs bundles, and we're going to look at properties of the fibration and the correspondences that appear. So I'm going to take away these, but we're going to keep in mind the way that we construct it. And one of the main motivations to think about this is that these fibres, like we said here, the generic fibres have some nice property, but the non-generic fibres are not that well understood. So what do we mean by non-generic fibres? We have this base, this affine space, that it's the base of the Hitchin fibration. There will be some, there will be some subspace, which will be the singular locus. And the way that we describe the singular locus, so I haven't told you what the singular point is, but what a singular point will be, it will be a point in the base which comes from a singular spectral cover. So singular locus is equal to points defining singular S. So you have all of those points, and over the top of this fibration, in these fibers, you have these tori, generically very nice compact abelian varieties, but over these singular points, it's not clear in general what you're going to have. You're going to have some sort of singular space that then you're going to compactify, but studying the points, studying the fibers over these blue locus for any group, it's still an open question. So you still want to understand. Those fibers are not fully understood. They're not even understood of what they are. For some cases, for instance, SL2C or SLNR, SLNC, people have shown that, for instance, they're connected, but what the geometry is not known. And for other groups, it's even less known. So one of the questions we want to ask is, what happens with these blue fibers? Can we understand, if not the blue fibers, can we understand a subspace of the blue fibers? And if we understand a subspace, can we describe them in some manner similar to this thing here? So if they are themselves not a Jacobian, could there be that inside there we can see copies of Jacobians, maybe of someone else? But can there be some other tori here that describes some particular nice space? And if we understood that, it would lead us to understanding things in a couple of other directions that are very interesting and which serve as motivation. One of which is Langlands duality. So let me remind you of how Langlands duality appears here. If you haven't seen Langlands dual groups, recall that for group G, if you have GC here, you have a Langlands dual group, which we're going to denote by GL, C. And the Langlands dual group is the group you get by taking the dual covariates, and the covariates of your group. So you're going to have, if you have SL and C here, you're going to have PGL and C. If you have, well, GL is self-dual, SP, 2NC, you'll have SO, 2N plus 1C. And if you have SO, 2NC, you'll be self-dual. This is just for you to remember the type of groups that correspond to each other. And what happens when you take the multispace for the dual group, MgCl, what you can notice is that it fibers over a space, a base, AgCl, which is actually isomorphic to the original one. In many cases, this is an identity, but in many cases, it's not an identity. So we'll just say it's isomorphic. And the duality between groups can be seen through Higgs bundles in two different perspectives that we're going to be interested in. From one perspective, we're going to see mirror symmetry appearing through what people call SYZ duality. So Strominger, Yau, and Zaslow propose that when you have toric fibrations that are dual to each other in some setting, so they were looking at Calabi-Yaus, the duality should mirror symmetry. Mirror symmetry should appear as a duality between fibers. So SYZ proposed duality is a duality between fibers. We had compact abelian varieties as generic fibers. Can we see the compact dual abelian varieties as fibers? Indeed, so they proposed this a decade or two ago. Hausel and Thaddeus showed it in the first case for SL. So Hausel and Thaddeus showed Thaddeus showed it for SL. Then later on, Donaghy and Pantev and Kapustin and Witten looked at these other cases and furthermore. But one important point that is not shown, so what they showed is that for these authors showed that for these groups, the duality between the fibers appears for the white fibers. So any regular fiber or generic fiber can be seen to be dual to the fiber in the dual space, sometimes through an identity, sometimes through a map in the base. However, what happens with the blue fibers? It's still an open question for all of those groups. So it's not clear what the dual fiber should be to a singular fiber. We want to approach that question by, instead of trying to understand what the whole fiber would go to in the dual setting, trying to understand what the nice red parts of the blue fibers go to. So that's one of the things that we want to do. So since an open question here, open question is what happens, what happens to blue fibers? Under the duality. We want to do the first steps. Understand. Nice. Smooth. Smooth varieties. And the way that we understand these nice smooth subvarieties and that then we can try to approach the question and conjecture what the dual objects will be is through these correspondences, Cayley and Langlands type correspondences. Before we start talking about those correspondences, one last piece of motivation that we're going to keep in mind, and that also fits within these questions about what happens with the blue fibers, is the relation through non-abelian Hodge theory to representations. So there's a couple things here we're going to say. There's the relation with reductive representations of the fundamental group of the Riemann surface into the group GC. So this is through non-abelian Hodge theory, work of Simpson, and Donaldson, and Corlett, and Hitchin, back from the 80s also. And we know that there is this correspondence here, there is an equivalent correspondence here, so anything that we ask, we can ask, what does it give us in terms of representations? Again, it's not clear which representations lie over these points. So understanding those ones will be interesting. And finally, we mentioned that there was two approaches to seeing this duality between the groups and the moduli spaces. We mentioned here one between the fibres, but the second one is between what people call the A model and B model of these objects, which means there's a duality, or there is a correspondence between objects, so the A model, or the Fukaya category of one space, and the Drag category of coherent sheaves of the other, the categories.
In the representation theory side, it's not clear what the analog of the Hitchin fibration is there, right?
It's not clear. Well, there is no Hitchin fibration, and so there's no way of understanding which ones in principle lie here. We could go through the representation theory and come to Higgs, but even still understanding which ones come here. Yeah. Categories. So the way that this will work, and this is something that will be interesting for us, is in terms of branes. So in terms of what people call branes. So branes from string theory or math physics in this terminology are spaces in your moduli space which support some hyperholomorphic sheaf. So let me put it here. Branes are spaces, subspaces, supporting hyperholomorphic sheaves. And depending on the properties that these branes have, they will be called A branes or B branes in one space or the other. So what we're going to use in order to define branes and to try to put the questions in context of branes is the following. It's going to be the fact that the moduli space MGC is hyperkähler. So because it's hyperkähler, it means that it has a sphere of complex structures and symplectic forms, and so we can choose and fix 3 of them that are compatible, and we can talk about A branes or B branes with respect to those. So hyperkähler, and thus we can fix I, J, and K complex structures. And omega I, omega J, and omega K, they're compatible symplectic forms. And then once we fix those, we need to say how we fix them. And we're going to say that I comes from the structure on the Riemann surface and that J comes from the structure on the complex group. And that's the convention we're going to use, which is the convention that people working on this duality were using. So we'll use that convention, and then when we talk about branes, we're going to talk about A branes and B branes. So an A brane and a B brane will be the following. An A brane will be a Lagrangian subspace, and B brane will be a complex submanifold. But because we have fixed 3 of them, we'll have 3 options to be Lagrangian with respect to, and 3 options to be complex submanifold with respect to. And so the options that we'll get, so in MGC, we have branes of type, and then we're going to have branes of type A, B, A, B, 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 A, B, and B, A. So what we're doing here is we're putting a triple of letters A or B with respect to this convention and saying this is a space that is Lagrangian with respect to omega I, complex submanifold with respect to J, and Lagrangian with respect to omega K, and so on and so forth. So the second version of mirror symmetry within our our picture here, our global picture where we want to put the results, is the correspondence between subspaces. So here we can actually say it's a correspondences between branes. Between branes. Which tells us, anytime you see from string theory, we will know that anytime we see here in particular a BBB brane, so something which is hyperholomorphic, a point is hyperholomorphic or the whole space is hyperholomorphic. Anytime we see a BBB, there will be a dual object here, which will be a BAA. This is a duality between types. So we're saying anytime you have a hyperholomorphic space supporting a hyperholomorphic sheaf, you have something that looks complex submanifold with respect to I, but Lagrangian with respect to omega j and omega k. And this should be the case for any such subspace, whatever it lies. It doesn't matter whether it lies on the singular or the regular fibers. So now we can ask further questions about these red spaces. What happens if these red spaces are BAA branes? Can we figure out then this duality for these BBB? The duality that is predicted by mirror symmetry, but which is not known for any of these examples. So I should say there is no proof of any correspondence between branes in this picture, partially because we don't have the correspondence for the blue fibers. So you can't make a global statement for any brane. If it lies in everywhere, you can't make it because you don't have these. But what you could do is you could try to conjecture where these subspaces should go, what should be the dual BBB. And that's what we're going to do in the last part of the talk. We're going to focus, maybe I'll just keep this picture here to keep the motivation in our heads. We're going to focus on these blue fibers, and we're going to try and figure out what happens with those red parts. Where can we look at them? And just as a tease, before we do that, of which other types of questions we could be asking here, since there's a few young people here, one thing that you could be asking when you see such a thing of fibrations and correspondences is try to wonder, okay, some people came up with these correspondences between Langlands dual groups, but is there any other correspondence that I could put here? In this Hitchin base, this A sub GC, this Hitchin base that has a singular locus, is there anything else that I could put here that I could fiber over the same base that would depend on Higgs bundles? So we want Higgs bundles. We want the moduli space of some group H. Is there any moduli space that fibers over the same base, and then when I look at this duality between objects, between branes, instead of taking me to what Langlands duality would be, or taking me BAA to BBB, that would take, for instance, BAA to BAA. So can I come up with a new fibration that fibers over the same base and takes branes of similar type? So BAA to BAA, BBB to BBB. If you want to know more about this, you should ask Steve Bradler here, because this is what happens with isogenies. So when you want to come up with such a fibration and such a correspondence, one thing that you can do is you can put a group here, and then we'll erase this picture, but what you can do is you can put a group here, say for instance SL4, and you can put your group H to be SO6, this is SO6C, SL4C, and when you look at the fibrations, they do fiber of the same space. And when you look at the BAA branes coming, for instance, from split real forms here, instead of going to some BBB space here, they will go to a BAA, coming from also split real forms in the dual space. And the map, instead of being a Langlands duality, so this map here, which is Langlands duality, the correspondences between groups, the map here is coming from isogenies between groups instead of Langlands. But we're not going to focus on that. We're going to focus on these blue fibers and what happens within the first picture. Remember that when we talk about singular fibers, we're talking about fibers whose curve is singular. So anytime that we have a fiber over a curve that is singular, that's going to be a singular fiber. So we're going to keep here our moduli space MGC, and we're going to keep our motivation of our fibration, where, just to recall, these fibers that we're interested in looking at are over points giving singular spectral curves. And the spectral curves S came, so S for a Higgs pair, for a GC Higgs pair, E phi, just generic GC Higgs pair, we haven't said anything. Recall that S is given by the zeros of the characteristic polynomial, so determinant of phi minus lambda times identity. So what we're saying is the blue parts are going to be any time that that algebraic equation defines a curve that's not smooth. And one of the cases that can happen is when your Higgs field has multiple eigenvalues. If your Higgs field has multiple, as a matrix, has multiple eigenvalues, then your characteristic polynomial will decompose, and your curve will be a decomposable curve. And so that for sure will lie in the blue. So note, in particular, multiple eigenvalues lead to points in singular locus. So we're going to be interested in points that have, or eigenvalues which are multiple for some Higgs fields, trying to describe these parts that are going to be inside. And one of the first cases that you can think of, what happens when I have multiple eigenvalues of a matrix, was the first eigenvalue you could have is 0. So let's think of Higgs bundles. So we will look at Higgs bundles with eigenvalues 0 of multiple order. So if you have an eigenvalue 0 of multiple order in a matrix, and you don't put any other condition for your matrix, generically what you'll have is the following. So generically, you'll have the characteristic polynomial of phi will be some lambda to some power, whatever the power of that eigenvalue 0 is, times a polynomial, p of lambda. Which in principle will have generically different roots. So generically different roots. So we want to focus on that case, and we want to go one step further and try to figure out whether there is any subspace that would be a brane, so it would lie inside these cases of having Lagrangian subspaces, that lies always inside the blue fibers, and that can be described in that way. And we're in luck. So what happens when you take, and this is just one case, and that's the case from a couple of months ago from the archive, but there's other cases that would be here. So this case, and this is with Baraglia, and you can look at for the paper recently. So you're going to take your moduli space, MGC, so I need to tell you what the complex group is. It's going to be the special orthogonal group of rank 2p plus q, C. So that q is going to be this q. This guy here is going to be degree 2p, because our matrix is 2p plus q. And I'm going to take the red spaces inside those singular fibers are going to be branes coming from real Higgs bundles. So consider the moduli space of Higgs bundles that are orthogonal but have preserve a Hermitian form of degree p plus q p. So SO p plus q p. So these are orthogonal Higgs bundles inside that moduli space. So I'm seeing this person here, this moduli space inside the big moduli space SO 2p plus q. See, inside that. What happens with this moduli space? First nice thing, this moduli space is a BAA brane. So it's a BAA brane, and when we look at the characteristic polynomial of Higgs fields there, what we get is that this is lambda to the q, so it has an order 0 q, and an order q 0, 0, and it has, the other polynomial is going to be lambda to a 2p plus a1, lambda to a 2p minus 2 plus a sub p. So what I'm saying here is that it's only going to have even degree, the polynomial. So generically, it has different roots, and here generically, in this case, it has plus and minus roots. So having even degree means that any eigenvalue that you have comes with a minus eigenvalue. So plus and minus a eigenvalue. So that's the particular case of this BAA brane. It's telling us that generically, all of the BAA brane, already for anyone who's in the brane, this polynomial will decompose. So for anyone in that brane, the polynomial decomposes, translates to, for anyone in the brane, you lie inside the blue fibers. Ask something, you don't know what, but you know that you're in the blue fibers. So the next thing you would like to do is try to understand how can we actually describe this space, this red space inside the blue fiber, as something which looks nice enough. So we'll use the, how much is it? 5 minutes? 3 minutes? 9 minutes. Right. I changed my watch and now I don't know whether I put it in advance. Cool. The next 9 minutes, what I want to tell you is how to understand these red spots in the blue fibers in a nice enough way, in a way that would come with Jacobians or prims. The way that we're going to do it is by forgetting that this is a bad curve, that this is a singular curve, and actually trying to come up with new covers that are smooth, but defined canonically through these objects. So this is the determinant, remember, this is the determinant of phi minus lambda, the identity, where phi is a Higgs field, which is an SO p plus q p Higgs field. Now I've told you that this is the characteristic polynomial, but I didn't tell you how these objects look like. So you had to believe me, but these Higgs bundles, the way they look like is the following. An SO p plus q p Higgs bundle is a pair, and it's a pair that looks the following. E is going to be V plus W, where V is P plus Q rank and W is rank P. So this is rank P plus Q. This is rank P. And our Higgs field is going to also have some structure. It's going to be generically have an eigenvalue 0 of order Q. So generically it's going to be 0, beta, gamma, or let me just put directly, beta transpose. Where I'm taking the transpose with respect to the orthogonal structure. And depending on how your conventions work with the orthogonal structure you take, you'll see in some papers they put a minus here, in some papers they don't. So we're not going to put a minus here. But this is the structure of the Higgs fields. They're off diagonal. The fact that they're off diagonal tells you in particular that this is going to be the structure of your characteristic polynomial. And the way that we're going to describe the fibers is the following. We're going to use this part of the polynomial. So generically, this part of the polynomial is going to be reducible and smooth. So generically, smooth, in particular irreducible. We're going to take that part of the polynomial and define a new cover of the Riemann surface. So defines a cover, and it's a rank 2p cover, so degree 2p. 2p to 1 cover, let me call it S, of the Riemann surface. How does it define it? We are just equating the whole thing to 0. Just like we used to define spectral curves, now instead of doing it for everyone, instead of saying we have a singular point that defines a singular fiber, we're saying a point here actually defines a smooth curve. So from this point here, we have smooth S. We're going to define another smooth cover using the same data. So this is the first thing we define. We're going to see here, we define 2 new covers of sigma. The 2 new covers of sigma are one is this one that we just introduced here, so the second one. And what is the first one? The first cover we're going to define, that we're going to use here, is going to just take advantage of the last point in this polynomial. So it's going to be a double cover. A double cover that I'm going to call C of sigma is 2 to 1. And it's going to be defined by an equation that's going to be the zeros of a new polynomial that I'll just construct from this one. So xi squared plus AP here. Depending on where I tell you that these objects live, you'll have a cover inside some space. So if I tell you that this is going to be a section of, for instance, the pullback of the canonical bundle to the P, then, and this is a section of the canonical bundle to the 2P, then you think of these inside the total space of K to the P. But we're giving meaning to these objects. We could do it without this meaning. That's my point here. We could give other meanings to these variables. We're just constructing a double cover starting from the information that we have here. Using this double cover that's smooth generically, and using this 2P cover that's smooth generically, we have 2 new covers on these from these points. So we have this point here is going to give us the smooth S and the smooth C. And so let me just give you the punchline of how these red things look like and how do you get them before the bell rings. The way that we're going to construct the aim that we have, so we want SO P plus Q P Higgs bundles that look like B plus W and phi. We want to recover these ones from these 2 covers. And what we're going to do is we're going to use what we call Langlands type and Cayley type correspondences. We'll have 2 correspondences coming from each of these 2 curves. These first curve here that we have, it'll be what we call a Cayley type correspondence. What we're going to do is we're going to take bundles which are on this curve C. We're going to take equivariant orthogonal bundles on C. And these equivariant orthogonal bundles of rank Q, the information they will be carrying is the 0 eigenspace. So we have here a 0 eigenspace. That will correspond to this guy here. So from here we'll get the 0 eigenspace. And we call them Cayley type correspondence because what you're getting from these 0 eigenspace is really a case to the P twisted Higgs bundle, and that's equivalent to what originally was introduced as a Cayley partner when P is equal to 2. So we're putting for any P and we're getting K to the P as our cover. And finally, from the other spectral cover, from this one that we have here, we're going to use a Langlands type duality. Langlands type correspondence. So when looking at Langlands correspondence, we mentioned that there was a duality between fibres, and when we talked about orthogonal groups, we mentioned that orthogonal groups were in duality with symplectic groups. And that's why we call these a Langlands type correspondence. What we're going to do is we're going to note that from this curve we can have a symplectic Higgs bundles. So there is, or take SP2PR maximal Higgs. But when you want to construct SP2PR Higgs bundles from a spectral cover, when you try to describe them in terms of fibres, what you realize is that actually is the Jacobian, when they are maximal, is the Jacobian of this curve that we have here. This curve has a little involution that sends lambda to minus lambda. Let me call this sigma. So it has an involution, and it's really points of order 2 from some old work that I had done. These Higgs bundles are that Jacobian, points of order 2, which is telling us, and then I'll just finish here, which is telling us that this red part that we have here is actually a union of a nice enough tori, or really points of order 2 in a tori, given by that Jacobian and points of order 2, times some rank Q orthogonal bundlers. So there's no way we can, unless there's extra conditions, there's no way we could abelianize, so we could get tori for every part of the red section. We will be able to only when there's extra conditions that kill these rank Q objects. But otherwise, these red parts inside the singular fibers will always be described by abelian data and non-abelian data. Thank you for listening.
Questions? So what's the BBB side of the picture
For these ones?
Yeah.
So our conjecture is that these objects are going to be dual to a BBB coming from the symplectic Higgs bundles. So for any Q, it will be the same space. That's what we conjecture. Yeah. For any Q, you'll have a moduli space, a whole moduli space of complex Higgs bundles, giving you the BBB brane in the dual side. And the same for all Qs. Yeah. For all Q evens and all Q odds.